Okay, so when we're talking about elastic potential energy, we're talking about things like springs, um, bungee cords, give you some examples, uh, rubber band. Those are some few simple examples. Elastic potential energy, basically, it's still stored energy, but it's in a, let's say, in a stretched or compressed state. I'm sure you've all, at some point in your life, either flipped someone with a rubber band or been flipped with a rubber band. If you want to really give somebody a nice smack with a rubber band, you stretch it far back, right? All of that stretch, that's considered potential energy until you let go of it, and then it's transferred to kinetic energy, and then it comes into contact with your arm or whatever, and you get some heat energy and some other kind of energy going on. But that stretch or compression is what makes the energy. And this stuff is called elastic. So I wrote down 3 super obvious things. Can you think of a couple more that would exhibit stored elastic potential energy? How many of you have ever played racquetball or tennis ball? Tennis. Have you ever watched, it's super cool, and sometimes they'll show it like on the, I don't know, those fancy tennis tournaments, like, I'm trying to remember the name of that really big one. Wimbledon, yeah, that's it. When that ball hits that, the netting, the screen, the strings, what does it do? Those things actually move with the ball. Have you ever seen it when one of them snaps? Yeah, there's a lot of force there. They will snap, but the ideal tennis racket has enough give that it absorbs that energy and transfers it back. All of those kind of spring things like a guitar or a violin or a tennis racket or a racquetball racket, all of those things are other examples. There's tons of them. Even the fabric that the base of a trampoline is made out of, sort of that nylon-y, but it's thick, even that has some elastic potential energy. And of course the springs along the side of the trampoline do. So you got to think about it and how we figure these things out. Because we're going to move over into lab here in a little bit. And at least we'll get your data tables and stuff set up today. I'm not sure if we'll move actually into the lab. But some things that you need to know. And we're going to use spring. The length of the spring when no force is acting on it is called relaxed length. So it's what the spring should normally be. The quantity of energy present depends on the amount of stretch or compression, it depends on what you're doing, of the spring from its relaxed length. So when we work with these in lab, we're going to be documenting relax and then stretch. When the string's in normal position, we're going to call it relaxed. You're going to put the mass on and it's going to stretch. That'll be your stretched length. What you really want to know about is the difference between the two. That's what really lets you do calculations. Okay, if you're a card keeper, grab it. And we can calculate elastic PE, and we will in lab. We write it like this: PE elastic is equal to 1/2 K times x squared. This is the distance of stretch or compression and K is called spring constant. Sometimes it's also called force constant. But it will have that word constant after it. So force shows up a lot of times. We know that from our problems. It's only K if it says constant after it. When I look at the force constant, I can be talking about two different kinds of springs. I can be talking about a flexible spring or I can be talking about a stiff spring. If I have a flexible spring, this should have a low spring constant. It's not very hard to stretch. If I have a stiff spring, it should have a high spring constant. Let's think about this formula for just a minute. Distance in this formula, it'll be measured in meters. Spring constant is a force in a distance, so it's measured in newtons per meter. Oh, shoot. There. So your x is measured in meters. That's your distance. Your k, your spring constant, is newtons per meter. We're going to define spring constant. Basically, we say it's a parameter that expresses how resistant a spring is to being stretched or compressed. Again, the higher the spring constant, the stiffer the spring. Think about that trampoline I was talking about just a minute ago. Anybody in this room have a trampoline? Did I ask you this question? Yeah. Tell me about the springs around the side of your trampoline. Have you ever tried to pull one of them? Yeah. Is it real easy to do with your hands? Heck no. They have a really high spring constant. I've got one. I don't have a trampoline spring. I couldn't find one. It's really hard to find springs to buy on a Sunday afternoon. But anyhow, I visited Home Depot and Lowe's yesterday trying to get springs. Nobody had a trampoline spring. But I do have one over there that's really stiff. It's hard to pull with your hands, just because I wanted you to see the differences. So remember your formula. PE elastic equals 1/2 K x squared. And we're going to use it when we go into lab. You're going to have to, in lab, find this, and eventually you're going to calculate K. That's going to take us a couple of days. Okay? So, I think that's all you need in your notes for us to move forward. Go ahead and put those away. Grab a computer and then go ahead and go back to your desk. We're going to kind of do this together. I can't remember if I